welcome to AI Paper Slop. Today we are looking at a really fascinating paper called Locate Anything, Fast and High-Quality Vision Language Grounding with Parallel Box Decoding.
Yeah, this one comes from researchers at NVIDIA, along with a few partner universities, and it is a massive leap forward.
It really is. So let's get straight into a 60-second executive summary for you. Right now, vision language models, or VLMs, are bottlenecking hard on visual grounding. Why? Because they rely on next token prediction to serialize two-dimensional bounding boxes into one-dimensional token streams.
Which is incredibly slow.
Right. It's painfully slow.
Right.
LocateAnything completely sidesteps this problem by introducing parallel box decoding. It predicts entire bounding boxes, like all four coordinates plus the structural tokens, as a single atomic six-token unit in one forward pass.
And they pull this off using a dual formulation training method.
Exactly, with a highly specialized heterogeneous attention mask backed up by a massive 138 million query dataset. For inference, they've engineered a hybrid mode that dynamically falls back to autoregressive decoding only when the model detects spatial ambiguity.
So the bottom line for your deployment pipelines, you get 2.5 times higher throughput, hitting 13.2 boxes per second, with better high IOU localization than current state-of-the-art quantized models.
That's the 60-second download.
Yeah.
But to really appreciate the engineering inside this architecture, we have to unpack the fundamental flaw in how current VLMs handle spatial data.
Yeah, I mean, if you're deploying a vision model to track a robotic arm or analyze a live security feed, you have to ask yourself, why are our most advanced parameter-heavy VLMs so agonizingly slow at simply drawing a box around an object?
Right. And it really comes down to how we frame the problem. We are taking a purely geometric task and forcing the model to solve it as a generative text problem.
Which makes no sense geometrically.
No.
Yes.
It's like asking a master painter to paint a masterpiece, but you force them to do it through a tiny keyhole, right? One single brushstroke at a time while blindfolded. And you have to wait for them to finish one stroke before you even let them think about the next one.
That is actually a highly accurate analogy for autoregressive decoding. I mean, standard VLMs formulate visual grounding by taking continuous spatial coordinates, normalizing them to a scale of 0 to 1,000, and then forcing the language decoder to output them token by token.
Which is just wild when you think about the compute overhead.
Oh, absolutely. Depending on the model architecture, they might use textual digits, literally spelling out the coordinate 1024 as the discrete text tokens 1, 0, 2, and 4.
Wow.
Or, they use quantized tokens, generating the top left X coordinate, waiting for the forward pass, generating the top left Y coordinate, waiting again, and so on.
But mathematically, a bounding box isn't a sequence of independent events. It's a single unified spatial entity. The top left corner is intrinsically coupled to the bottom right corner.
Yes, exactly. And forcing a model to generate those coordinates one at a time completely ignores that coupled reality. It underutilizes the structured correlation among the coordinates.
And it creates a massive latency bottleneck.
Right, because during inference, you are running a full forward pass for every single number. It's terribly inefficient.
Now, I know people have tried to speed this up before. Using generic multi-token prediction, or MTP, we've seen models try to predict like 3 or 4 tokens ahead to save compute.
Yeah, standard MTP has been around.
So why doesn't that standard MTP approach solve this bounding box latency?
Well, because generic MTP is completely structure agnostic. When you use generic multi-token prediction, you're basically telling the model to group tokens into arbitrary chunks based purely on where they happen to fall in the sequence.
With zero regard for their actual semantic meaning.
Exactly, zero regard. So let's say you tell the model to predict the next 5 tokens simultaneously. In a complex visual grounding task, those 5 tokens might randomly slice right through the middle of an object's data.
Oh, I see.
Yeah, you might get a chunk that contains, say, the bottom right coordinate of a dog, followed by the end box token, the start reference token for the next object, and then the text label cat.
So the model is forced to find patterns in completely arbitrary, misaligned slices of data.
Exactly. And because those slices don't represent any consistent underlying structure, the model learns unaligned cross-boundary patterns. It starts relying on unreliable co-occurrences.
Which means it hallucinates.
Big time. In practice, this means the model starts hallucinating coordinates that literally bleed across object categories. You end up with a system that tries to infer the spatial boundaries of a cat using the momentum of the spatial coordinates it just generated for a dog.
That's hilarious. but also terrible for accuracy.
Yeah, the error propagation is disastrous. It completely tanks your localization accuracy.
Which means if arbitrary slicing fails, the only logical engineering solution is to just stop slicing the box at all. You have to treat the bounding box as an indivisible unit. Throw away the keyhole and just give the model a square stamp.
A square stamp. I like that. And that is the exact core premise of Locate Anything. To execute that stamp approach, they really had to rethink the input-output architecture from the ground up.
Let's talk about that input side first.
So on the input side, they use a MoonViT vision encoder operating at the image's native resolution. And this is a critical detail.
Right, because most models scale down or crop images to fit a standard tensor size.
Yeah, but doing that instantly destroys the fine-grained spatial mapping you need for precise bounding box localization. So they preserve that native resolution, extract the visual tokens, and map them via a two-layer MLP projector.
Straight into a Queen 2.5 language decoder.
You got it. And then on the output side, they reorganized everything into fixed-length, box-aligned blocks. The paper defines this length L as exactly 6 tokens.
Okay, wait. Why exactly 6?
Because 6 tokens cover the entire anatomical structure of a bounding box. They call this the box block. It is strictly defined. It must start with a box structural token, followed by the 4 quantized spatial coordinates by 1, y1 by 2, and y2, and it must terminate with an end box token.
So those 6 tokens are treated as a single atomic unit, predicted in one parallel step. But a vision language model doesn't just output boxes, right?
Mm-hmm.
It outputs text labels, system prompts, negative confirmations. How do you handle all of that if your architecture is basically hard-coded to process everything in rigid 6-token parallel chunks?
Well, you standardize the rest of the vocabulary to fit the mold.
Oh, really? How?
To maintain uniform tensor shapes for parallel decoding across the entire sequence, they defined other functional blocks. You have semantic blocks for the text labels describing the object,
Yep.
negative blocks to explicitly signal when a queried object isn't present in the image, and end blocks for sequence termination.
But what if the word is short? Like if a block doesn't naturally require all 6 tokens, say the text label is simply the word car, which is only 1 token, what happens to the other 5 spaces?
But they're just filled with null padding tokens.
Okay, conceptually, making the box an atomic unit beautifully resolves the fragmentation issue we saw with generic MTP. But if I'm looking at this from an architecture standpoint, I see a massive red flag here.
Oh, yeah. What's the flag?
Quinn 2.5 is a causal language model. It's fundamentally built to predict the next token based on the past. So, how do you train a purely causal language model to predict 6 tokens simultaneously without totally destroying its underlying causal reasoning capabilities?
That is the exact hurdle that makes this paper so technically impressive. Because you're right, if you just force-feed parallel outputs into a causal decoder during training, you will lobotomize the model's inherent language logic.
Right, it would just forget how to read sequentially.
Exactly. So to solve this, the researchers introduced a dual formulation training strategy. They trained the model jointly on 2 aligned representations of the exact same ground truth simultaneously.
Wait. They feed it the standard sequential version and the parallel block version in the exact same training pass.
Yes. They construct a single, massive, concatenated sequence. Think of it as a long freight train of data.
Okay, paint me a picture of this train.
First, you have the visual context tokens, followed by the text query tokens. Then you attach the standard next token prediction sequence, the traditional token-by-token output.
Right. And finally, you attach the blockwise multi-token prediction sequence. They are all linked into one continuous sequence for the forward pass.
But if the standard sequential tokens are right next to the parallel blocks in the same sequence, why wouldn't the standard tokens just, look ahead at the parallel blocks and cheat the loss function? It seems like a recipe for catastrophic data leakage.
That is exactly what would happen if you used a standard causal attention mask. And that's why the heterogeneous attention mask they developed is the linchpin of this entire system.
Heterogeneous attention mask sounds intense.
It's basically a highly complex traffic controller. It physically routes which tokens can access which matrices in the key value cache. Let's break down its 3 distinct routing behaviors.
Okay, let's hear it.
First, for the standard next token prediction stream, they enforce strict traditional causal attention. Tokens in this stream can only see the shared context, like the image and the query, and their own preceding tokens.
So the mask places a hard algorithmic wall preventing them from attending to anything in the parallel block stream. Exactly. Zero data leakage.
Okay, that makes sense. It preserves the model's standard language capabilities because it doesn't even know the parallel stream exists. What about the rules for the parallel stream?
For the parallel stream, they use a two-tiered masking approach. Across different blocks, meaning block 2, looking at block 1, the flow is strictly causal. The active block can see the shared image context and all previously committed blocks, but it cannot see into the future.
And I guess that historical visibility is absolutely necessary so the model doesn't predict duplicate bounding boxes for the same object, or miss objects entirely.
Precisely. It needs to know what it already stamped down.
But inside the block itself, if you wanted to predict all 6 tokens at once, it can't be causal.
Right. Inside the block, the causal rules are suspended. They use bidirectional attention within that 6-token unit.
Oh, wow. So all 6 can see each other?
Yes. All 6 internal tokens can attend to each other simultaneously. This fully connected intra-block interaction is what allows the model to capture the complex geometric dependencies, how the top left corner relates to the bottom right corner, and resolve all 6 tokens at the exact same moment.
That is wild. The model is optimizing both the standard sequential loss and the parallel block loss in the exact same forward pass under completely different attention rules. It's incredibly elegant.
It really is a beautiful piece of math.
But let's step out of the math for a second and look at the physical GPU reality of this. You are concatenating all these sequences. And for the parallel stream, you are padding out every short text label with null tokens to force them into 6-token blocks.
Yeah.
The sequence lengths for different training samples are going to be wildly different. I mean, if you're paying by the hour for a 256 GPU cluster, using naive padding to make your batches uniform is basically setting money on fire. You're spending massive amounts of compute multiplying zeros.
Oh, you'd be wasting over half your compute on empty space if you did that. The system-level engineering required to train this efficiently is honestly just as vital as the dual formulation math.
So how do they fix it?
To prevent that compute waste, they implemented a technique called stream packing. They set a hard target budget of 36,864 tokens per batch.
Why that specific number? Seems oddly precise.
It's the mathematically optimal sequence length to maximize hardware utilization on their specific NVIDIA GPU architecture without triggering out-of-memory errors.
Okay, fair enough. But how do you hit that exact budget without wasting space with padding?
They use an algorithm called best fit buffering. Imagine you were playing a very high-stakes game of Tetris. The stream packer holds a pool of oversized pending data samples in a buffer.
Right.
When it's assembling a training batch, it scans that buffer for the largest single sample that will perfectly fit into the remaining token budget of that specific batch. It's a best fit decreasing heuristic that empirically achieves over 95% packing efficiency.
Okay, but if I'm packing a GPU like a Tetris board, eventually I'm left with awkward tiny gaps, right? And the massive data samples sitting in my buffer are never going to fit into the tail end of a batch.
That's a valid concern.
How do they keep those massive samples from just sitting in the buffer forever, starving out the training pipeline?
They engineered a countermeasure for that called Big Rock's first seeding. The very moment a batch is finished and dispatched to the GPU, the packer begins the next batch by immediately seeding it with the absolute largest sample currently sitting in the buffer.
I see.
Yeah, by placing the biggest rocks in first and using the smaller samples to fill the gaps at the end, nothing gets starved out.
Okay, so the sequence lengths are packed efficiently, and you aren't wasting GPU hours. But by using stream packing, you've created a new, frankly, terrifying problem.
Uh-oh. What's that?
You've built these massive, dense Franken sequences that contain multiple, completely unrelated images and queries stacked end to end. And every single one of those samples requires that complex, heterogeneous attention mask we just talked about.
Yeah, that's true.
Standard flash attention relies on contiguous, uniform memory tiling. If you throw irregular sample-dependent masks at it, it breaks down, doesn't it?
It completely fails.
Yeah.
Standard flash attention assumes that the causal masking pattern is uniform across the entire sequence. It cannot handle a packed sequence where, one segment requires strict causal masking, the next segment requires bidirectional interblock masking, and the next segment belongs to a totally different image and shouldn't attend to the previous segment at all.
So how do they train it?
To solve this, they had to integrate match attention across their cluster.
Match attention. How does that fix the memory tiling issue?
So MAG-attention is a distributed attention framework specifically designed for ultra-long contexts with irregular masks. It basically decouples the attention computation from the assumption of uniform contiguous memory.
Okay, so it handles the irregular boundaries.
Right. It dynamically partitions the key value cache based on the actual token boundaries of the packed samples and routes the attention computation according to the heterogeneous mask.
That's really clever.
Yeah. Stream packing maximizes the raw token level utilization on the GPU, and MAG-attention ensures that the complex routing rules are processed efficiently without the unrelated samples cross-contaminating each other.
It's a massive stack of engineering just to make the training feasible. Which honestly brings us to the ultimate question. How does this perform in the wild?
The real test, yeah.
We got it trained efficiently, it's predicting 6 tokens at once, and it's supposedly 2.5 times faster. But in real-world deployment, you always face the exploration-exploitation dilemma. Where does predicting 6 spatial tokens in parallel fall apart? Like, complex scenes must confuse it.
They absolutely do. Predicting 6 tokens in parallel is fast, but it's a fundamentally harder probability task than autoregressive prediction, where you can condition each step on the last.
Makes sense.
The authors are very transparent about this, actually. They identify 2 specific failure modes for parallel decoding. The first is format irregularity.
Format irregularity. What does that look like?
This occurs in complex scenes where the model is transitioning between dense object categories. It hesitates, and that uncertainty manifests as literal syntax errors within the block.
Like it forgets how to format the tokens.
Exactly. It might erroneously mix structural tokens and coordinate tokens. For example, it might try to output an n-reference token right in the middle of a bounding box coordinate sequence.
Oh, wow. It's like a software engineer trying to write code, getting distracted, and putting a closing bracket right in the middle of a variable name. It just breaks the compiler.
That's exactly it. The second failure mode is spatial ambiguity, and this is triggered by densely packed, highly regular grids.
Give me an example of a dense grid in this context.
Think of a drone looking down at a parking lot full of identical cars, or a robot navigating a supermarket shelf packed with identical cans of soup.
Okay, yeah, that's tough.
In these dense spatial layouts, the parallel approach can actually blur the spatial boundaries. Because it's trying to resolve all coordinates at once, the probability distribution flattens out.
And what happens to the output?
It ends up predicting an intermediate coordinate that sits right in the empty space between 2 objects. The resulting bounding box has a very low intersection over union, or IOU. It's basically drawing a box around nothing.
But if you're deploying this in a warehouse robot, you can't just accept malformed syntax and boxes that highlight empty air between shelves. How do they fix it without losing all the speed gains?
This is where their hybrid solution comes into play, and it relies on an adaptive, real-time next token prediction fallback.
Oh, interesting. So it switches modes on the fly.
Yes. During inference, the model defaults to fast mode, utilizing parallel decoding. But under the hood, it is constantly monitoring its own spatial confidence. They engineered a highly specific mathematical trigger.
What's the trigger?
If the top 1 coordinate token's probability drops below 0.7, and the maximum to minimum difference among the top 5 coordinate tokens exceeds 80 in that 0 to 1000 normalized space, the ambiguity trigger fires.
Wait, let me make sure I understand that math. It's essentially checking if the loudest voice in the room is quiet, under 0.7 probability. And if the top 5 competing guesses are all clustered together within an 80-point spread.
Exactly.
So it's mathematically detecting its own hesitation.
That is a brilliant way to phrase it, yes.
Yeah.
And when that hesitation trigger fires, or if it detects a formatting syntax violation, it takes immediate action.
What does it do?
It instantly discards that single compromise block. It reverts to the last verified, accurate prefix, switches the architecture into slow mode, and auto-regressively decodes that one specific block token by token using standard next token prediction.
Oh, wait, if you're hitting the brakes, throwing away the block, and starting over in slow mode every time the model gets confused, doesn't that completely defeat the purpose of parallel decoding?
Yeah.
I mean, you're adding the latency of the failed parallel pass on top of the slow sequential pass.
You would be right if the model triggered the fallback constantly. But it doesn't. The fallback is extremely rare. acting only as a targeted safety net for the most difficult spatial boundaries.
Okay.
We can see this clearly in their ablation results on the COSIO dataset. If you force the model purely into slow-mode standard token-by-token next token prediction, it runs at a painful 3.9 boxes per second, yielding an F1 accuracy score of 52.1.
Right, very slow.
Now, if you force it purely into fast mode, the throughput skyrockets to 16.9 boxes per second.
That's a huge jump.
It is, but accuracy drops to an F1 of 49.6 because those spatial ambiguity failure modes drag down the average.
Where does the hybrid mode land?
It hits the absolute sweet spot. Hybrid mode achieves 13.2 boxes per second with an F1 score of 51.6.
Wow.
Yeah, you are retaining nearly the maximum possible accuracy while operating at over 3 times the speed of the standard method. You only pay the latency penalty exactly when the scene geometry demands it.
Okay, the fallback mechanism is an incredibly smart piece of engineering. But a fallback relies on the model knowing what a dense grid looks like in the first place, right? So it knows when to lower its confidence. You can't teach a model the nuances of a dense supermarket shelf just by feeding it standard single-object internet images.
No, definitely not.
What kind of data set did they have to build to calibrate this?
To fuel this architecture, they curated a data set called LocateAnything-Data, and the scale is staggering. We're talking 138 million queries, generating 785 million bounding boxes across 12 million images.
That is massive.
And they didn't just dump all 138 million queries into the model at once. They used a very deliberate, 2-stage supervised fine-tuning process.
How did they split it up?
Stage 1 utilized the massive 138 million mixture to build a broad, comprehensive baseline for spatial awareness. This included object detection, user interface grounding, OCR, and layout analysis.
And stage 2, I assume that's where they address the dense grids.
Precisely. In stage 2, they reduced the general broad domain data down to just 20% of the training mix and heavily over-indexed on extremely dense, complex datasets.
Like what?
We're talking about datasets like MOT20det, which is used for multi-object tracking in crowded scenes, and SesquiU110K, which is composed entirely of images of densely packed retail shelves.
Ah, I see the strategy.
Right.
By over-indexing on those specific data sets in the final fine-tuning stage, they are explicitly hardening the model against the spatial ambiguity failure mode we discussed.
Exactly.
They're forcing the parallel decoder to practice resolving spatial boundaries in the exact environments where it naturally wants to blur them.
It's a perfect alignment of targeted dataset curation, patching, and architectural vulnerability.
So bringing this all together, what is the core takeaway for you, the listener? If you are a machine learning engineer building embodied agents, programming robotic pick-and-place systems, or developing real-time GUI navigation agents, LocateAnything represents a fundamental shift in how you deploy spatial models.
It really does.
By breaking the one-dimensional serialization bottleneck and treating 2D bounding boxes as atomic bidirectional units, this team hasn't just sped up an old process. They've shifted the entire speed accuracy frontier. You no longer have to compromise, choosing between a model that is spatially accurate but agonizingly slow, or a model that is fast but prone to hallucinating coordinates.
And, if we step back and look at the broader implications for the field of AI, this paper proves a really vital point. Tightly coupled, multidimensional geometric data should never be forced into the one-dimensional paradigm of language tokens.
Right. It's a square peg in a round hole.
Exactly. It should be treated natively as bidirectional atomic blocks. And that leaves us with a truly fascinating question to explore.
What's that?
If this block-wise dual formulation architecture with its heterogeneous attention masking works this perfectly for two-dimensional bounding boxes, could we apply this exact same methodology to instantly decode complex 3D spatial meshes?
Oh, wow.
Or multi-joint robotic arm trajectories? What about applying it to rigidly structured code blocks, decoding an entire function in a single forward pass? It strongly suggests that when it comes to structured data, we have only just scratched the surface of what parallel decoding can achieve.
I couldn't agree more. We've finally taken the blindfold off the painter and handed them the square stamp. Now we just have to see what else they can build with it. Thanks for joining us on AI Paper Slop, and we'll see you next time.